This is the first lesson in topic 4, lesson 4-1, solving systems by graphing. So our driving question today, what is a system of linear equations and how can we solve this system by graphing? So the first thing you need to know is that a system of linear equations is a group of two or more linear equations. So it's several equations clumped together. The point or points where all of those equations in the system intersect is the solution. Let's look at an example of this. Okay, so here we have a system of linear equations. I see two equations up at the top. One is y equals 2x minus 1, and the other is y equals negative x plus 5. So my first equation, what has a y-intercept of negative 1? So is it the blue one or the green one? It is the blue one, because again it has the y-intercept of negative 1, and also it has a slope of 2. Remember that 2 has an invisible 1 under it, so it means we went up 2 and over 1. Then in green we have the second equation with a y-intercept of 5 and a slope of negative 1, so it went down 1 over 1 each unit. So we notice there is an intersection point here. That point is coordinate 2, 3. Because it's the intersection point, it is also our solution. So our answers for these types of problems won't be one specific number like x equals 5 or y equals 7, but it will have both numbers, an x and a y, written inside an ordered pair or coordinate. Now, since there is a solution to this system, we call it a consistent system. And since there's only one solution, exactly one solution, we call it independent. Now, there is times where there's more than one solution, and that's actually going to be our next example. But before we go to that, and I want to draw your attention to the orange font in the top right hand corner. So notice that we mentioned that it's the intersection, it's the solution, but what does that really mean? That means that if I plug in those numbers for x and y, 2 and 3, then the statements or the equations will be true. So on the top one, 2 times 2, which is the x value, is 4, minus 1 is 3. My y value is 3. So the left and right side of the equation of the equal sign match. On the second one, once again I plug in 2, negative 2 plus 5 is 3, and that was the y value. So if it only works for one of the equations but not the other, that is not your solution. That point has to work for both or all of the equations in the system for it to be your solution. And the way that you'll hear it worded is that the equations are true. It's like a true or false statement. Does 3 equal 3? Yes, so it's true. Here's the next example. In this one we have 2y equals x minus 6 and negative y equals 3 minus 1/2 x. So notice it's not already in slope-intercept form. It doesn't have to be, but I do have to somehow figure out a way to graph it. In the last topic you learned several methods for graphing. You can use whichever one you want to. But today I'm actually going to solve for slope-intercept form so I can figure out what it is. So I've gone ahead and done that. And if I divide the first equation by 2, I get y equals 1/2 x minus 3. And the second equation, I already had y pretty much alone, but it had a negative. I made it positive, but that means I have to change the signs of everything else. So I end up with negative 3 plus 1/2 x, or if you rearrange them, it's 1/2 x minus 3. Right off the bat, you might notice something about these two equations, but I'm going to go ahead and start to graph them. So I've gone ahead and graphed the blue equation, y-intercept of negative 3, and then it goes up 1 over 2 if I follow my slope. And now I've graphed my second equation in orange. So if you didn't notice it before, maybe now you're seeing they're actually the exact same equation. So that means that the lines lie right on top of one another. They are overlapping. So what does this mean for our solutions? Because I'm supposed to find where they intersect, but they're right on top of one another. So every single point on this line, and it doesn't have to be right on a grid line, it's any point that lies right on top of both lines, is considered a solution. But there's no possible way that we can write down every single point. So what we say is that there are infinitely many solutions. So when they're right on top of each other, every point on that line is a solution, and there are an infinite number of those solutions. So because it's a system and there's a solution, it may be infinitely many solutions, but there's still a solution. We call it consistent still. But this time we use the word dependent, because they're, and I'm trying to think of the best way to explain this, but when they're independent, it's kind of like one of the lines has nothing to do with the other, which is why you only get one intersection point. When they're dependent, they have everything to do with one another because they're exactly the same. So that's when we have infinitely many solutions. Here is our third and final example. So in this one, I have y equals 3/4 x plus 2. And I also have y equals 3/4 x minus 2. So what do you notice about these two equations? You may have noticed that they have the same slope. Now, hopefully you remember, what does it mean when two equations have the same slope? Well, now that we've graphed them, you might remember that that means that they're parallel. The exact definition of parallel is that they're two lines that will never intersect. So we need an intersection to have a solution. So therefore, we write no solution, because there will never be a point where these two lines will intersect. So because there is no solution, we call this system inconsistent, opposite from the ones that did have solutions. And we can't say whether it's independent or dependent because there's no solution at all. So we don't even talk about the other description words. We just say it's inconsistent. So let's recap today's lesson. First, you have to graph each equation. Once you graph the equations, determine if there's one solution, infinitely many solutions, or perhaps there's no solution at all. And one thing that I briefly touched on but wasn't very clear about was that you can double check your answer by plugging in that coordinate, the x and y values, into all the x's and y's of each equation. So just a few notes. When you're graphing each equation, you may use your preferred method. I think a lot of times the easiest is to get it into y equals mx plus b, so you can graph your y-intercept and then follow the slope. But many of you became very good at finding the x and y intercepts, and you can graph it that way as well. On number 2, remember that if there's an intersection like an x, then that's one solution. If the two lines are overlapping, that's infinitely many solutions. And if the lines are parallel, there is no solution. We use the word true, that each statement should be true. I'm talking about number 3 here. Meaning that when you plug in those x and y values into the equation, the left side of the equal sign should match the right side of the equal sign. So if it says like 10 equals 10, that is true. So each of those statements should be true if it truly is the answer or the solution to your system of equations. Also, just to let you know, there is a way to graph and find the intersection in the calculator. You'll be shown this in class. I don't mind if you use the calculator to help you do these things, but you definitely should know what all of these things mean and how to find the answer by hand. Don't just rely on the calculator. All right, I'll see you in class. Make sure you take your notes. I'm going to be checking them. And take good, thorough notes with the graphs and images.